2212 Lab 5 presentation. The purpose of this lab is to simulate the ideas of induced current, magnetic flux, and Faraday's law. The materials needed for this lab is GlowScript, the coding program, a dipole magnet, a roll of tinfoil, and a timer. And so the first part of this experimental procedure is to create a tinfoil tube as our conductor. And here we have the initial values, which is the length being 37 centimeters, the width of the outside of the tinfoil being 2.2 centimeters, and the inner radius in the center of the tinfoil tube being 1.3 centimeters. And the next part of the experiment is to drop a dipole magnet down the tube 5 times and average out the times for the magnet to fall through. And our average time was 0.542 seconds. And so the next part of this lab is to calculate the time it takes for a magnet to go through the tube using these physical principles here. So the first physical principle we have is Faraday's law, which is calculating the flux, the change in flux to find the induced current in the tube. And then a second physics concept we have is the Busev law, which is used to find the magnetic field to use in Faraday's law. And the last concept we will be using is Newton's law, and it's used to calculate, we'll be using it to calculate total force as well as velocity in time. And another physical principle we will be using is the current equals EMF over R. And so the first part of the coding experiment we had to do on GlowScript was to initialize the variables. So we initialized the variables here, being the length of the dimensions of the tube that we found here, and the mass of the magnet and the dipole, the magnetic dipole moment, which we found in our last lab to be 2.963. And with those values, and then we created two functions here to be used in our GlowScript code. The first function being the function to calculate the magnetic field, and the next function to calculate the magnetic flux calculate the magnetic flux. And so using these functions, we were able to start by calculating the magnetic field of the tube right here using the function. And once we calculated the magnetic flux, we were able to calculate the current within the tube right here by dividing magnetic flux by the resistivity that we have of the tube. And then this part of the code starts to simulate the magnet going through the tube, which will be shown in our final expression. And once we have that done, we added together the total magnetic field, and with that total magnetic field, we were able to calculate the total magnetic force. And using the total force and Newton's laws, second and third law, we were able to calculate the total magnetic force that was used on the magnet, and from there we were able to calculate the final velocity it had and the final position, and then we were able to find the change in time. And so the experimental time we found, was 0.542 seconds, as we saw in the previous slides. And the time that was calculated, the time actual, was 0.521 seconds, and which is not very far off. So we did our experiment pretty accurately, and as you can see from this diagram was the magnet falling through the tube, and as you can see from this graph right here, we were able to look at the velocity of the magnet through the tube. At this point, it was just starting to enter the tube, and then the velocity went up, and it plateaued for a little bit. So we assume that that there was no net force within of the magnet within the tube because because the the magnetic force the force from the magnetic flux canceled out the force of gravity, and so therefore there was no acceleration. And once it came out the bottom of the tube, the velocity returned to what it was at the beginning. And some additional questions we had were, what if resistivity of the conductor was to be reduced as close to possible as zero? And how would the dynamics of the falling magnet change? So the equation we used a lot in this lab was, an equation we used in this lab was I equals EMF over R. And so since the formula was of calculating I was equal to EMF over R, the current would be much larger if the resistance was lowered to zero, since I and R are inversely related. And so what if holes or slots were cut into tubes? How would this affect the ring currents in your model? Okay, so as we can see from the formula right here from the beginning, we see that N is actually within the EMF formula. And since N was in the formula, and if holes or slots were to be cut off from the tube, the number of loops will technically go down, and that would cause the EMF to go down in turn because they are proportionally related.